So, in the last lecture I was trying to urge you to recollect some things from your nuclear physics class, and here in this lecture I continue with what I started with in my last lecture. That is, I am talking a little bit on the fusion process, okay. And I am concentrating all on the nucleus. I am not saying anything about the electrons which are outside, okay, for the moment. Everything is to do with the nucleus, the neutrons and the protons, okay. So, this was the binding energy curve here, okay. What is the significance of this binding energy curve? Why is it so important? That is because if you see this green line here and this green portion, and all the energy here, I mean all the elements which are here release energy either by decay, they just decay, or they go through a fission process and then a decay. So, there is a fission process because they are all trying to be iron here. So, they are decaying and they are decaying and they attain this portion. So, these are kind of I would say not slightly, maybe you could say it this way, slightly maybe loosely bound electrons, sorry, not nucleons. So, they are trying to achieve this position of a tightly bound nucleon. Okay. So, they disintegrate and form smaller ones which are tightly bound, and in the process that excess energy is given out. Okay. Now, the same thing is happening even on the other side, on this blue side. All these the nucleons like deuterium, tritium, hydrogen, all of them are trying to fuse together. 2 of tritium will come together, or 2 of deuterium will come together, or deuterium and tritium will come together, and they will fuse and form a better bound nucleus, and in the process that excess energy it will just give up. So, fusion is also giving you energy and fission is also giving you energy. Okay. The fission process has been mastered very well, and you have reactors and bombs and such things, but the fusion process is not mastered that well. You do not have a controlled way of obtaining energy. So, people have been trying for 4 decades, much or maybe perhaps more than that, trying to achieve a break even condition. It is not that they have not achieved fusion. Fusion has been achieved, it has been checked, and but then is it a break even condition? By break even I mean the amount of energy that you are putting in to achieve fusion, are you getting equal amount of energy from the fusion process? That is called break even. That is still lacking. Okay. So, the thing is you have got to get break even condition, and on top of that you have got to get excess energy. Okay. So, here I will be talking about the efforts already put in by scientists for so many years, and it is an ongoing process. And I would say it is the most exotic use of lasers to attain fusion in a controlled fashion and to get the break even condition. Okay. So, let us go a little bit ahead to talk about the fusion process. So, here what I have shown is a DT atom. D is deuterium, T is tritium. Okay. So, these two will fuse together and come here, and it will release an alpha and it will release a neutron. Okay. And this alpha and the neutron carries away that excess energy. It is not as if the alpha is separate, neutron is separate and some separate energy is coming out. No, these are the ones that are carrying away that energy, that excess energy which has been caused due to the fusion process, and you have to utilize this energy which is embedded in this. So, D plus T gives alpha plus N. So, 3.5 MeV the alpha is carrying and 14.1 MeV the neutron is carrying. So, total is 14, 15, 16, 17, 17.6 MeV you get the total with one fusion process. Okay. So, that is a lot of energy in one fusion process. Here I just write down the equations. 3.5, this is the same as here. Now, I have put it down as the hydrogen atom. So, this is 2, deuterium is a isotope of hydrogen which has 2 in the nucleus, neutron and proton. Tritium has 3 nucleons in the nucleus, proton plus 2 more neutrons. Okay. So, these two will fuse together and it will give an alpha particle. Alpha is same as helium particle. Alpha is the same as this, only thing it is doubly ionized. That means, when you talk of the helium atom, it is stripped of its electrons, of course. It is an ionized, doubly ionized atom. Okay. So, helium here is that alpha, and then one neutron. Neutron is a single neutron which is carrying away 14.1 MeV energy. You could have a similar fusion reaction, but with DD here. D plus D will give you a tritium 1.01 MeV plus a hydrogen which is 3.01 MeV. DD will be H21 plus H, that means isotope of hydrogen, these two are identical, and it gives you a tritium H31 plus a hydrogen atom. Okay. So, this is what you are getting. So, here the total energy that comes out in case of a DD reaction is 3 plus 4, around 4 MeV. Okay. So, here the energy is much more, here it is lesser. So, this is more this has been experimented with more, okay, D and T reactions. So, we will confine to the DT reactions now. Okay. So, this is the fusion process, the concept. Now, how should you bring a deuterium and a tritium atom close together? So, in order to bring the nucleus close together, you have to bring those atoms close together, and these atoms have electrons revolving around. Okay. So, it has to overcome that Coulomb energy. So, you have to push them together so that it overcomes that Coulomb energy, and then only they will fuse. Okay. So, this requires a big push. How will you do it? So, there is this repelling force of these electrons. So, you overcome that and you bring them together, and then the next step is for the nucleons to fuse together to give you that released energy. It is generally done in a small pellet in case of inertially confined fusion, ICF. Okay. So, what is done is there is DT gas. Okay. This is a pellet, it is a round circular thing, it is a DT gas, deuterium tritium gas, and then you have this blue layer, one more layer, it is a sphere, spherical object, and one more layer of the fuel layer. Fuel layer is again DT, but it is solidified, frozen or solidified. This part is the gas part, and this part is the frozen DT fuel. And then you have one more capsule here, which is called the capsule ablator. Okay, so this may not be D and T, it is a high Z material. Okay. you will slowly come to know the use of this, high Z material, so that when the laser falls on it, it disintegrates into a plasma. So, that is what we want. It easily disintegrates into a plasma. Okay. So, this is a schematic of the target capsule. So, this is the target and you have to hit it with a laser, and not one laser. It has to be hit symmetrically from all directions by the lasing beam. Okay. So, these are the stages of inertially confined fusion. 4 stages are there, and all happening in a nanosecond time scale. I have just separated them out in 4 stages, that is how it works, just to show you the working, but it is happening in a nanosecond time scale. So, as you can see in this first sphere, this is that pellet sphere which has the DT gas, DT frozen part and the high Z material on the outside, and all these arrows shows you the laser beam which is hitting it equally from all sides of the sphere. So, in stage 1, the laser beam strikes the outer layer of the fusion target, so that it evaporates almost immediately, forming a plasma. So, it is made out of this high Z material. Okay. So, and the energy is so high, the heat is so much that it evaporates into a plasma. Okay. And high Z material becomes plasma very easily. So, that is why the high Z material is coated over the sphere. The outer shell of the capsule is burned into plasma and blasts off. So, this total part is become plasma, this yellowish part. Okay. It has become plasma, and it is not going to be contained there, it will blast off, it will just move off. And plasma is made out of positive and negative ions, and they are going to repel all the positive ones, they are just going to repel each other and just blow off. And this blast off is something like a rocket, See this red arrows which I have shown here, this is the kind of a rocket action. So, this plasma is blasting off outside, but it is giving an equal and opposite reaction here, just like in a rocket, the fuel goes down and the rocket goes up, and this is the direction in which the fuel is moving now. Okay, that outer part of that fuel, okay, which is the solidified DT, okay, or frozen deuterium and tritium. Okay. This results in a force in the second stage, results in a force in the opposite direction, causing main fuel layer of the pellet to be forced inward by an inward propagating spherical shock wave through the pellet to the middle. Okay, it is not just a force, ordinary force, it is a shock wave. Okay. The shock waves happen in very short time. It is a kind of force, but shock all within a short time, it is a large force. That is why it is called shock wave, which goes right up to the middle of this pellet. Now, in the third stage, subsequently during the final part of the capsule implosion because it is happening inward not outward of the pellet, okay, part of the capsule implosion, the fuel core reaches 20 times the density of lead and 100 million degrees Kelvin. So, you can imagine the temperature that it has reached because of this implosion, okay, and fusion reaction starts. Okay. Now, in stage 4 here, this actually the fusion reaction is taking place, that is what it shows, the burn of the DT gas. Stage 4, if the rate of such a reaction is high enough, the heat generated will cause the thermonuclear burn to spread rapidly throughout the compressed fuel. Okay. So, in this stage, in the third stage, you have compressed the fuel 20 times the density of lead and 100 million degrees K. And the rate of such a reaction is high enough, that means it is quick. Then the fuel, the compressed fuel will start burning. Start burning means start fusing, you know, the fuel starts fusing, that is what we want. The D and T are fusing. You have brought them close together, it is fusing now and slowly releasing in the fusion process, it is releasing the energy. Okay. So, what has to be achieved is this released energy more than all the effort that you have put in to get this compression. Perhaps not completely as yet, but definitely a lot has been done. If say you haven't reached a break even in fusion, but you have learnt a lot about the laser plasma interaction. You have a plasma layer here, all here, this plasma layer. So, again depending on that plasma layer, the laser will penetrate inside or not penetrate inside depending on the density of the plasma. There is something called the critical density, beyond which the laser cannot penetrate. So, a lot of research has been done on studying the laser plasma interaction. So, there are enough problems to be solved as yet in order to get a controlled break even fusion. Okay. So, here let me see, there is something called the Lawson's criteria. This is the criteria for fusion to take place. Okay. Now, you need to, first of all, you need to bring these two atoms together. Then you have to keep them close together over time, so that they fuse and then they release that energy. So, Lawson came up with a approximate, what should I say, an approximate equation like this, where n tau should be greater than 10 to the power 14 centimeter per centimeter cube per volume into second. N is the density, okay. N is the density, okay. And tau is the time over which the plasma is brought close together. So, generally suppose say suppose I have a plasma, say it has 10 to the power say 15 such ions and electrons moving about per centimeter cube. Okay. Then the time will be, if you just put that value, tau will be somewhere close to 0.1 second, okay, 14 by 15 per centimeter cube. So, 10 to the power minus 1, so 0.1 second. So, if I have a plasma of particles 10 to the power 15 per centimeter cube, then tau will be of the order of 0.1 second. So, that means all these particles have to be kept close together for 0.1 seconds, then only that fusion will take place. So, that is called the Lawson's criteria. It is very difficult to achieve this. People have achieved it in a tokamak, which is something different from ICF. People have achieved it. For a short time it may not even have gone up to 0.1 second. But so this criteria has to be modified for the laser. In case of the laser, in case of the laser, they are all pulsed lasers, okay, and this part is not really achieved by the laser. So, suppose the laser is in nanosecond 10 to the power minus 9 seconds. So, your tau is reduced, so your density has to increase. Okay. So, your density has to increase. Now, how much? So, suppose 10 to the power 9 seconds, density is 10 to the power 14 upon 10 to the power minus 9. So, 14, 15, 16, 17, 18, 10 to the power 23 per centimeter cube. So, your density has to increase. Why do I take this in nanoseconds? Okay. It has some relation to the size of the pellet. The pellets are generally very small. Okay. Pellets are maybe about 1 mm pellet size. Pellet diameter or pellet radius is around 1 mm. And the shock wave that I spoke of in the previous lecture, the shock wave that is traveling through this pellet is at the rate of the speed of sound, which is somewhere close to 10 to the power 6 meters per second. So, depending on the pellet size and the shock wave that is traveling, the inertia of the fuel, inertia, as you know, anything in motion remains in motion, anything is stationary remains stationary. So, the fuel inside which is burning has an inertia, it remains stationary, but at the same time there is so much pressure from the plasma to throw it out, to disintegrate, because these are two opposing forces, and if you are able to keep them till 10 to the power minus 9 seconds, it is very good. But the point is how? It is with the use of lasers. Okay. Now, these till now I have described lasers as just the oscillator part, but really these lasers where you need joules of energy, very high 500,000 joules of energy. It will not come out of a single oscillator. You will need chains and chains of such amplifiers. So, generally they are called MOPA chains, master oscillator. So, I will have an oscillator. And then this goes on to one amplifier, where the energy output of the pulse from here goes into one amplifier and then gets amplified Again, this much energy is not enough. It has to go into another amplifier which is larger than this, so that it can extract energy, and so it goes on. So, these are called laser chains. master oscillator power amplifier. Okay. Just to give you an idea, for laser fusion process, these laboratories are huge, as big as a factory. Just have a look at this picture here. This man is a small thing here, and all these are the laser chain, part of the laser chain. Such huge installations are required for that fusion process. Okay. And the pellet itself, and all of them have to be directed evenly on this small pellet, and this pellet is tiny, 1 mm. Quite often you will see a picture in Wikipedia or even in textbooks. They will show you that pellet. It will be sitting on a finger just to show you how tiny it is. It will be sitting like that if this is a finger. Okay. And you have kept this finger near your eye. You will come across this very often on the internet. Okay, this is the pellet, this small thing, it is that tiny. To emphasize how tiny it is, to bring home the point, instead of just saying 1 mm, you show this picture. So, all these lasers have to be directed onto this equally, and there are very, very stringent conditions on the laser pulse. So, it should have a proper pulse duration, as I have told you here. It should be focusable to a very tiny spots. So, beam size cannot be something like in a semiconductor laser, where there is a strip of laser light. It has to be focusable to a small spot, and it has to be a nice clean pulse. So, there are quite a few stringent requirements for the laser itself, and that is what my focus will be in the coming few lectures. What is the speciality of these specific kind of lasers?